Hi, this is Kate, and this is the third video for week 4 of Math 23. Last time we mentioned how useful it is to find an eigenbasis for the domain of a linear transformation. And now let's talk a little bit more about the properties of an eigenbasis. First, we see that even if all the eigenvalues are distinct, an eigenbasis is not unique. I think in video 1 I mentioned that any eigenvector in the basis can be multiplied by a non-zero scalar and remain an eigenvector. That was in the first video when we were talking about how to find eigenvectors and eigenvalues, and we were sort of reducing them down, quote unquote, to their simplest form. So it's important to note that if you consider all the possible scalar multiples of eigenvectors, there are a bunch of eigenbases for a given linear transformations domain. Another one is that eigenvectors that correspond to distinct eigenvalues are linearly independent, and we will be proving that as your first proof for this week. And the third thing is that if a matrix is symmetric, eigenvectors that correspond to distinct eigenvalues are orthogonal. That is pretty interesting. Now, here's of course probably the burning question. What if there is no eigenbasis? Well, when does that happen? Remember we talked about when there was an eigenbasis in the previous video, but maybe you don't have a polynomial that has simple real roots. What then? So let's take a look at some of these situations. It's easiest for us to discuss the 2x2 case here because things get exceedingly computationally complicated in higher dimensions, but these sort of illustrate the major properties and issues that come up adequately in the 2x2 case, and the computation is totally doable, so that's great. So A is a 2x2 matrix. If a real polynomial that we get does not have two distinct real roots, like I said, then it either has a repeated real root or it has a pair of conjugate complex roots. So we know that an eigenbasis exists if and only if we have real distinct roots. So when we don't have real distinct roots, the two options are a repeated real root or a pair of complex conjugate roots. Okay, the first case, when we have this repeated root, where here's what our polynomial looks like. We have p of t is equal to t minus lambda squared. So when we make that a polynomial being a function of our matrix, we have a minus lambda I squared is equal to 0. And setting n equal to a minus lambda I, that means that n squared is equal to 0. And this matrix n, this a minus lambda I, is what we call nilpotent. Now, we can rearrange this statement, this n equals a minus lambda I, to solve for a, which means that a is equal to lambda I plus n. And so a squared is equal to lambda I plus n squared. And when we carry out this squaring, we have lambda squared I plus 2 lambda n. And of course, we do have a plus n squared on here, but n squared is 0, so this is all that we're left with. And so it's actually pretty straightforward to prove by induction that a to the k equals this lambda I plus n to the k, which is equal to this. And if you have time, it's a pretty straightforward proof by induction, but definitely, if you're up for practicing your inductive skills, you should definitely go ahead and give it a try. It's a fun one. So in the case of a repeated real root, this is how we end up expressing high powers of the matrix A. A little more complicated than if we have an eigenbasis, but still works. All right, now for the meaty part. We have two roots that are complex numbers, and they're complex conjugates of each other. So in this case, we have a 2x2 real matrix A. It has eigenvalues a plus beta I and a minus beta I. Then it can be expressed in the form where A equals P C P inverse, where C is this conformal matrix, and P is what we call a change of basis matrix. It's a little bit of a complicated concept at first. You're definitely going to have to work at it. I'll talk about it when we get to the part where we introduce the matrix P at the very end. And it takes some time until it starts clicking for you and making more sense. But let's dive right in here. All right, so since a conformal matrix is almost as easy to raise to a given power as a diagonal matrix, this representation is pretty useful for us in terms of trying to express A raised to a very high power. So here's an algorithm for constructing the matrices C and P. So suppose the eigenvalues of A are A plus beta I and A minus beta I, A plus IB, or normally you'll see sometimes C in notation if you're looking at another text. A complex number expressed like this means the exact same thing. All right, then A has no real eigenvectors, and for any real W, we will find the following polynomial. And this is just saying T minus, and here's A minus beta I, and here's T minus A plus beta I. And that is equal to, once we expand this out, T minus A squared plus B squared. So when we turn that into a polynomial in terms of our matrix A, that's equal to A minus A, which is a scalar, times I, the identity matrix squared, plus B squared, also a scalar, times I, the identity matrix, and that's going to give us 0. Or we could also say that A minus AI over B squared equals negative I. How do we get there? Just a little bit of algebra, honestly. Subtract this term onto the right-hand side and then divide by B squared, and that's it. So now we have this fact. And this in particular, this matrix here is very useful for constructing a new basis. We're going to construct a new basis, which will not be a basis of eigenvectors, but it's still going to be very useful to us. Obviously, this is when we can't find a basis of eigenvectors, so it will not be a basis of eigenvectors. So we set v1, the first vector of our new basis, equal to e1, the first standard basis vector. v2, the second vector of our new basis, is going to be equal to a minus ai over b times e1. Now note that this is not a scalar, this is a matrix. A minus AI over B acting on E1. So these are not scalar multiples of each other, in case you were already like, whoa, 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 I thought we were creating a basis. We are. Let's go with it. So then, if we take A minus AI acting on V1, that is going to give us the same thing as B times V2, just by virtue of how we've constructed V2. And so what that means is by rearranging this, by expanding that out, we now find that A acting on V1 is equal to little a times V1 plus B times V2. Similarly, this fact, A minus AI over B acting on V2, is equal to A minus AI over B squared acting on V1. Again, by virtue of how we've constructed V1 and V2. And we also know that A minus AI over B squared is equal to negative identity matrix, negative 1 times the identity matrix. So this A minus AI over B squared acting on V1 will give us negative 1 times the identity matrix times V1, which is just negative V1. So putting this side and this side all together, we can multiply over by B, and we get that A minus AI acting on V2 equals negative BV1. And so when we expand this out and we isolate the term A acting on V2 on one side, we have that equals A times V2 minus B times V1. Now, here is what is really important. Remember that with linear transformations, when we're wondering what a linear transformation does to the standard basis vectors, we just look at a given column of the matrix that represents the linear transformation. Now, know that the matrix C here, with respect to the new basis, this matrix that represents A is this conformal matrix. What this is saying is that, okay, what happens to my first new basis vector, v1, when A acts on it? Up here, this says I get A times v1 plus B times v2. A times v1 plus B times v2. Then the second column here corresponds to what happens when A acts on my second new basis vector. Well, I get A times v2 minus B times v1. Here's the coefficient on v1, the first new basis vector, and the coefficient on v2, the second new basis vector. So again, that's something that you're probably going to rewind and listen to again and again, but this is with respect to the new basis. This tells me the coefficient of the first new basis vector. This tells me the coefficient of the second new basis vector when A acts on each new basis vector. Then we need to define P in the quote-unquote usual way with columns v1 and v2. Then A equals P, C, P inverse, and the matrices P and C are real. The question now is, what is P doing? Let's take a look. First, before we even get into it with P, let's look at how we usually write vectors. And I want you to change the way you think about them. I mentioned this earlier, but here normally you have a vector written with respect to the standard basis, and unless stated otherwise, a vector is written with respect to the standard basis. Instead of thinking this is 3 to the right and this is 4 up, or x1 to the right and x2 up, I want you to think of these as the coefficients of the standard basis vectors. So when you look at something like this, what this is really doing is encoding the following. It's saying, hey, I want x1 times e1 plus x2 times e2. That's what a vector like that means. Now, when we look at something like P, what this is actually doing is telling us this is how to write a vector with respect to the new basis in terms of the standard basis. What do I mean by that? Well, imagine if we had this P act on 1, 0. It would extract v1, right? v1 here is written with respect to the standard basis. We didn't do anything differently here, but this 1, 0 is written with respect to the new basis. It says 1 times v1 plus 0 times v2. When I multiply, have P act on that vector, it translates this shorthand, which is in terms of the new basis, the v's, and spits out this v1, which is in terms of the standard basis. And so let's take a note of that. It's hard to keep things straight in our minds, but if P takes a vector that's written with respect to the new basis, the v basis that we constructed in this problem, and spits out how to write those vectors in terms of the standard basis, P inverse is going to do the opposite. P inverse will take a vector written in terms of the standard basis and translate it and tell us how to write it in terms of the new basis, the v basis. I'm going to say that again one more time slowly. P inverse takes a vector written in terms of the standard basis, and when P inverse acts on that vector, it spits out a vector whose entries will tell us the necessary coefficients on v1 and v2 to create that old vector. It tells us the coefficients in terms of the new basis. P does the opposite. It takes vectors written in terms of the new basis, those are the coefficients on the new basis vectors, and it spits out whatever the necessary coefficients should be on the standard basis vectors. So when you look at something like P inverse CP, P inverse takes a vector written in the standard basis and it writes it in terms of the new basis. Then C is the actual the same transformation as A, but written in terms of the new basis, where we remember up here we talked about what happens to V1 when A acts on it. Here are the coefficients on V1 and V2. That creates the first column. What happens to V2 when A acts on it? Here are the coefficients right here. So C is the same transformation as A, but expressed in the new basis. And then P takes us out of the new basis and goes back to the standard basis. It's a very difficult concept. Be patient with yourselves. We're going to do an example in class, but it is definitely the way for us to be able to express A in a way that allows us to take higher and higher powers of it more easily, computationally speaking. You might be wondering when we're ever going to need eigenvectors and why I would need them. Let's take a look at some of the applications of eigenvectors. One is certainly Markov processes. Suppose that a system can be in one of two or more states, just like we did before the volleyball problem, and we have these transition probabilities. And so we have this particular matrix that we can set up that tells us exactly what the likelihood is of either of the two states. We went through this earlier in the class. A lot of the time we're interested in a high number of iterations of the process, and so we're taking this matrix A and raising it to a very high power. Frequently, that's not computationally easy to determine, but it is if we can diagonalize A. So that's one application of eigenvectors. And in particular, if there's a stationary state into which the system ends up settling down, it does correspond to an eigenvector with eigenvalue 1. That's what we were sort of looking at when we were watching those vectors converge, so to speak. Another example of eigenvectors coming in handy is when we have a 2x2 matrix that represents reflection in a line through the origin. Well, if we have a particular direction vector v, that when this reflection matrix acts on v, it returns v, that means v is in the line of reflection. So v actually ends up being an eigenvector with eigenvalue 1. Similarly, if you have a vector that's perpendicular to your line of reflection, then when you reflect it, you're going to get exactly opposite that vector, and so that original vector is an eigenvector of this transformation associated with eigenvalue -1. Similarly, if you have the same thing basically happens if you have a 3x3 matrix that represents reflection in a plane instead of a line. If you have a vector that is in the plane, any vector, generally that's a two-dimensional subspace of vectors, so they all have eigenvalue 1 if they're in the plane. And then if it's a normal vector, a vector that's perpendicular to the plane, if we reflect it through the plane, we'll get the exact opposite of that vector, and so that's going to be an eigenvector with eigenvalue -1. Another example is linear recurrences and Fibonacci-like sequences. So in computer science, it's really common that the first two terms are specified and then you're given this sort of formula to find the terms that follow in a particular sequence. And the most famous example of this is the Fibonacci sequence, where we say, okay, A0 is 1 and A1 is 1, and then every next term is a sum of the previous two terms. And generally, when every next term is some linear combination of the previous two terms, the way to write a matrix that gives not just an but an plus 1 is to have the matrix 0, 1, b, c act on it, where b and c are the coefficients on a sub n minus 1 and a sub n that give the recipe for the next term. And of course, in the case of the Fibonacci sequence, b and c are 1. But you frequently want to know, what is the 23rd item in the sequence? What's the 24th item of the sequence? And it's really hard to take this matrix to higher and higher powers. So the easiest way to raise this to the nth power is to diagonalize it, as we did earlier. And the very last thing is solving systems of linear differential equations. And this is a really important topic in physics, and we'll actually return to it after we talk a little bit more about infinite series and incorporate a bit more calculus into our language of mathematics. But it definitely comes up as a place where eigenvectors and eigenvalues become very useful in determining what the outcome is of a linear transformation multiple times on a vector. That's it for week 4. If you have any questions, please let me know.